desert up here, my dear. It won't be long now. It won't be long now.
Hey guys, so now let's look at our tracker program. So first I selected my frames to be 52 to 80 as the car is already in motion and it cuts out the acceleration. With my car being the point of mass, I chose the car to move in the positive x direction on the x-axis, with the y being the vertical axis and the x being the horizontal axis. Our graph over here that the program produces is linear, and in a few moments I'll compare it to a model made by Idle. The values taken from tracker are especially useful. This is our final position, this is our initial position, this is our final time and our initial time, and we can use these four values. We can actually use any of these values as long as we go from one point to the next, and we will always get the same velocity. But here I use these four values. With the formula delta v equals delta x over delta t, which is the change in position over the change in time giving you your velocity, I found out our velocity to be 0.42 meters per second. Let's go ahead and look at how the video looks. Last, before we leave tracker, let's go ahead and note down the last recorded time, which was 0.934 seconds. And we're going to need that in our code for Python to let the program know when to stop. Let's go ahead and examine our code for idle and look at our prediction. So we're basically going to start at the system properties and the initial conditions. Our system was the little toy car, and the mass of it was 34 grams. We converted that to kilograms to plug it into here because this program reads SI units. So it becomes 0.034. Next we look at the initial position, which is 0.008, which we got from tracker. The initial velocity is also a value that we obtained from tracker. It's 0.42 meters per second. The time step here is delta t equals 0.01. When we deal with Newton's second law, we're dealing with a short amount of time, so in our case it was around 1 second. So we want this delta t to be even very small compared to that, and here I took around 1/100th of a second. Next we go to the calculation loop, and this was our total time, or the last time recorded, which was 0.934 seconds. And by putting in this value in the calculation loop, or the while loop here, it tells the program when to stop. The total net force was 0. This line right here represents Newton's second law. This is the initial velocity, this is the final velocity, and because the net force is 0, all of this disappears, and the final is equal to the initial, meaning constant velocity. This is this equation right here is basically a position update. This is the final position, this is the initial position, this is the velocity of the ball times the change in time. And this basically gives us the position of the ball in respect to time. We basically unhashtag this to graph the plot, and down here we unhashtag this to close the file and to run it. Now let's go ahead and look at how it looks. And it looks just like we wanted it to look. It started at a point and moved to the right on the x-axis, just like our item did in tracker, the way I wanted it to. And this is our model data. Let's look at how it looks compared to the experimental data. So our experimental data is the dotted blue line, and although they're not the same, they're pretty close. They're both pretty linear, except for the experimental is a little shaky, it goes up and down. But the reason for that is probably because the car didn't actually move in an extreme straight line like it would be predicted. It started a little bit to the left or the right and moved to the left. Like we can see, it's like it started over here, ended up over here, and that probably is the reason why it's not exactly the same. Overall, the experiment was pretty successful.